over the past several years, the concentration of carbon dioxide in the Earth's atmosphere has risen at an alarming rate, thereby causing an increase in global temperatures owing to the greenhouse effect. Numerous approaches have been proposed to tackle growing CO2 levels, from minimizing consumption of fossil fuels to capturing and sequestering CO2. Although these are promising avenues, CO2 conversion in particular is attractive as it has the potential to provide useful end products. Systems for capturing and converting carbon dioxide from power plant emissions could be important tools for curbing climate change, but most are relatively inefficient and expensive. Now, researchers at MIT have developed a method that could significantly boost the performance of systems that use catalytic surfaces to enhance the rates of carbon sequestering electrochemical reactions. Such catalytic systems are an attractive option for carbon capture because they can produce useful, valuable products such as transportation fuels or chemical feedstocks. This output can help to subsidize the process, offsetting the costs of reducing greenhouse gas emissions. In these systems, typically, a stream of gas containing carbon dioxide passes through water to deliver carbon dioxide for the electrochemical reaction. The movement through water is like this, which slows the rate of conversion of the carbon dioxide. The new design ensures that the carbon dioxide stream stays concentrated in the water right next to the catalyst surface. The researchers have shown that this concentration can nearly double the performance of the system. The results are described in the journal Cell Reports Physical Science. Carbon dioxide sequestration is the challenge of our times. There are a number of approaches, including geological sequestration, ocean storage, mineralization, and chemical conversion. When it comes to making useful, saleable products out of this greenhouse gas, electrochemical conversion is particularly promising, but it still needs improvements to become economically viable. The researchers found that the bottleneck turned out to involve the delivery of the carbon dioxide to the catalytic surface that promotes the desired chemical transformations. In these electrochemical systems, the stream of carbon dioxide containing gases is mixed with water, either under pressure or by bubbling it through a container outfitted with electrodes of a catalyst material such as copper. A voltage is then applied to promote chemical reactions producing carbon compounds that can be transformed into fuels or other products. There are two challenges in such systems. The reaction can proceed so fast that it uses up the supply of carbon dioxide reaching the catalyst more quickly than it can be replenished. And if that happens, a competing reaction, the splitting of water into hydrogen and oxygen, can take over and sap much of the energy being put into the reaction. Previous efforts to optimize these reactions by texturing the catalyst surfaces to increase the surface area for reactions had failed to deliver on their expectations because the carbon dioxide supplied to the surface couldn't keep up with the increased reaction rate, thereby switching to hydrogen production over time. The researchers addressed these problems through the use of a gas attracting surface placed in close proximity to the catalyst material. This material is a specially textured gas-philic superhydrophobic material that repels water but allows a smooth layer of gas called a plastron to stay close along its surface. It keeps the incoming flow of carbon dioxide right up against the catalyst so that the desired carbon dioxide conversion reactions can be maximized. By using dye-based pH indicators, the researchers were able to visualize carbon dioxide concentration gradients in the test cell and show that the enhanced concentration of carbon dioxide emanates from the plastron. In a series of lab experiments using this setup, the rate of the carbon conversion reaction nearly doubled. It was also sustained over time, whereas in previous experiments the reaction quickly faded out. The system produced high rates of ethylene, propanol and ethanol, a potential automotive fuel. Meanwhile, the competing hydrogen evolution was sharply curtailed. Although the new work makes it possible to fine-tune the system to produce the desired mix of product, in some applications, optimizing for hydrogen production as a fuel might be the desired result, which can also be done. By concentrating the carbon dioxide next to the catalyst surface, the new system also produced two new potentially useful carbon compounds, acetone and acetate that had not previously been detected in any such electrochemical systems at appreciable rates. In this initial laboratory work, a single strip of the hydrophobic gas-attractive material was placed next to a single copper electrode. But in future work, a practical device might be made using a dense set of interleaved pairs of plates.